I realized that. What's it such a harsh? Wait, what is it?
Oh, so we're just taking the same information from area and expanding it to volume. So yesterday, what we did yesterday is, it's basically the core concept. So if you know that, then we're just extending it to volume.
And what they say. Like, it's just like, you know.
Oh, yeah, so if you want to graph this, you have to divide it as y is equal to plus or minus the square root of x. So there's three graphs. You got y equals square root of x, y equals negative square root of x, and the y equals x to the power. So we got this graph, and this graph. That's the only way to get this to show up.
So you can't put in y squared and have. No.
Well, yeah, you can't put it in y squared.
Or like x squared.
Well, if you do x squared, then it'll look like this. It's not going to quite be the graph that this is showing.
Okay.
But
You're saying we're gonna have to graph that problem, because I was having trouble with that. Yeah.
on the test, I will graph it for you, so you can just. look at it. Yeah. All right, so. So again, I want to, thank you. I want to go back to briefly to what we talked about yesterday, how if your graphs are to the left and to the right of each other, we have to do right minus left. And if you're forced into a right minus left situation, you know that your equations have to take on the proper form. Your equations will look like x equals, what you insert will be y's, and then your bounds have to be in terms of y as well. If you're doing top minus bottom, then you can leave everything as a function. Your expression will take on the form of y equals. Your top and bottom expressions will be in terms of x, and your bounds will be in terms of x. Okay. So this is really the core concept for the remainder of this unit. If you understand how right minus left works and how top minus bottom works. If you know what's needed for right minus left versus what's needed for top minus bottom, this I think is the most important concept. And if you can get that information down, then really we're just taking this information and the same information and we're just adapting it to volume. Whether it's this method, washer method, or cross section, it's the same piece of information. You're just taking that information and putting it into a different formula. Okay. So I think that's the most important and also the most difficult part is understanding what's needed for right minus left, what's needed for top minus bottom, and not mixing things up and knowing exactly where things go. Now for area, sometimes you're able to choose either top minus bottom or right minus left. But with volume, you're kind of forced into one or the other because there's certain things in the problem that's going to cause us to have to do things either with this method or this method. Okay, but with area, we can kind of pick and choose depending, assuming that we're able to algebraically get to the other side. Like these problems are good because we're able to see things from both perspectives. But with volume, there's certain things that will force us into one way or the other. All right, so let's talk about that. Let's go to page 9. Okay, so first I want to kind of get the conceptual part down. Okay. So let's go back to talking about area. Okay, so recall finding area under the curve y equals square root of x between 0 and 4. So here's the square root of x graph. I'll put that here. between 0 and 4. So let's say I just want to find the area of that region. This is nicely set up for top minus bottom. Okay. Depth integral will just be from A to B, top graph minus bottom graph. What's the top graph? Yeah, square root of x. What's the bottom graph? 0. Okay. And I talked about how we want to have this imaginary rectangles extending from one end to the other, right? We're stacking these infinitely thin rectangles and we're adding up these infinitely thin rectangles to find the area. Is the top of every rectangle that you can imagine hitting the same curve? Yes. Is the bottom of every rectangle hitting the same graph? Yes. So all we need is one area formula and that will get us there. Okay. So let me write out what we already know. And I want to point out a few things along the way. So depth integral from 0 to 4, because those are our bounds. Top graph is square root of x minus 0 dx. Okay. Now I want to talk about this here. That square root of x minus 0, okay, represents the height component of these rectangles. Okay? And the dx represents the width. And we talked about the width, how this infinitely thin, right? Infinitely thin rectangles that we're adding. But you see the height and width component, and that reminds you of area, right? Width times height is area. So we're basically accumulating all these rectangular shapes from one end to the other. And we have a two-dimensional answer, right? At least when we go through this process, we get a two-dimensional answer. Okay. So if we were to finish off this problem, we go through power rule. Evaluate our bounds from 0 to 4. Okay, 4 to the 2/3. That's the same thing as square root of 4. The 2 is basically taking the square root. So square root of 4 is 2. 2 cubed is 8. 8 times 2/3 is 16/3. And this is an area calculation, so it's unit squared. Right, so I wanted to kind of make sure that we have this background set, that we understand this concept, because we're going to take this area, we're going to extend it into a three-dimensional object. Everybody good so far? Okay. Now, we're going to take the same shape. Okay. So hold on, let me reread this here. Essentially, the integral notation allows us to add infinite numbers of differently sized rectangles to form the area calculation. Okay, so you can imagine all these different size rectangles depending on the curve. As it moves higher, we get higher rectangles, but we don't have to worry about that. The formula takes care of it. Okay. Now, with this method, what we're going to do is we're going to take this region that we created. Okay. We're going to take this two-dimensional region that we created. Okay. And we're going to rotate this 360 degrees around the x-axis. So imagine taking this two-dimensional shape that we had from above, and we're rotating it all the way around. And as it rotates, we want to create an object out of it. And you can kind of see it turns into like a circular bowl, right? Do you guys see that? Okay. So basically what we're doing is we're always going to start with a two-dimensional shape. We're always going to be rotating around a line. We're always going to get a circular or circular-based object. And we're going to be finding the volume of that object. Now, we don't have to really worry about what the graph looks like. We just have to know certain things about it. And we just have to be able to pull information very much the same that we did from above and just insert it into a new formula. So let me talk about so is everybody good with that? You know, I have trouble drawing it and I don't expect you guys to draw it, but I want you guys to see and understand the visual concept. You see how this turns into a three-dimensional object. Okay, good. Now, before we said that these were rectangles, right? we're still going to use this information. We're still going to do this top minus bottom here. But now, instead of this being the height of a rectangle, now this is going to be representative of a radius of a what? Of a circle. Okay, so that's really the thing here, is that now this is going to represent the radius of a circle. We're going to call it big R of X. Okay. So now, instead of adding infinitely thin rectangles to achieve an area, we're not going to add infinitely thin circular disks to achieve the volume of this object. Now, the actual disk will be a lot thinner than what we have here, but I just want us to be able to see that these are, basically really, really thin disks. Okay. So I have this highlighted here. So this now represents the radius of a circle. And before, dx represented the width of rectangles. But now dx is going to represent the width of these circular disks. Okay, so I'm going to go over here again, call this big R of X. Now, if you remember, what is the area of a circle? Area is what? Pi r squared. So I'm going to adapt it and say that area is pi big R of X squared, because it's going to represent, we're going to have something representing that width, because you see that the radius is going to be changing all the way across because you're going to have all these differently sized disks. Now, what I want to show you is that pi r squared, this is a, how many dimensions is pi r squared? 2-dimensional, right? Area is 2-dimensional. But then we're going to add in this dx, this width component. So you got the area and the width. That's going to create a 3-dimensional calculation. So here's our volume formula. We're still going from x1 to x2. We're still going from the furthest left bound to right bound. We could go from 0 to 4 if we wanted to. And then we have the area component, pi big R of X squared dx. So before it was just width, height, and width. And now we're extending it to add a 3rd dimension. So we have an area, which is 2-dimensional. We have a width, which is a 3rd dimension. So area times width gives us volume. But I want us to just understand that we're still gathering the same information. We're just basically putting it into a different formula to achieve a 3-dimensional calculation. Okay. So instead of thinking of these top minus bottom as heights of a rectangle, we now want to consider the top minus bottom as the radius of these circular disks. Okay, one thing I left out is the problem is going to indicate to you what your axis of revolution is in terms of what you're rotating around. So in this case, the axis of revolution is the x-axis. So we're rotating around the x-axis. So I like to do like this circular shape to indicate that's the direction that I'm rotating in. And axis of revolution. I like to abbreviate it using AOR. So that's that's the way that I'm going to do it. I'm always going to put a dotted line with that rotation notation there to indicate that's the direction that I'm spinning this 2-dimensional shape in. Okay, so let's go ahead and do this problem here. Okay, so we're going to do this problem below. There's something else, sorry, I do want to point something else here is look at this shaded region and look at the axis of revolution. Okay, do you see any gaps between the shaded region and the axis of revolution. There's no gap, right? Because it's a flat surface up against a horizontal line. So that's just something that I want to point out to you, that that's what's going to make the difference with later on when we talk about holes in the graph. So if you see a flat surface up against a flat surface, up against the axis of revolution, you know that we're going to do this method. But if it's a curved region up against the axis of revolution, then there's going to be a hole or a gap created, and we have a separate formula for that. So again, you don't really have to know what the graph looks like or what the object looks like. You just have to pay attention to does the object have a flat surface up against the axis? So all these problems, we're gonna have a flat surface up against the object, flat surface up against the dotted line, against the axis of revolution. Okay, so just like with area, we're going to have top minus bottom versus right minus left. And what's going to tell us which to use is your axis of revolution. Okay, if your axis of revolution is horizontal, then you're able to do top minus bottom because your radius is going to be drawn perpendicular to your axis of revolution. Okay. If your axis of revolution is vertical, then we have to extend the radius horizontally. If it's horizontal radius, then we'll do right minus left. And just like from before, if it's right minus left, we have to adjust all of our formulas. Our bounds have to be adjusted. Our equations have to be adjusted. Okay. All right, so we're going to basically do this problem, okay, with this space below. All right, so example 1, find the volume of the solid formed by rotating the curve y equals square root of x around the x-axis between 0 and 4. So here's my shaded region. Okay, so it tells us our axis of revolution. It says around the x-axis, so that tells us where the axis of revolution is. AOR is at y equals 0. So put a dotted line right on the x-axis. Notice that your shape has a flat surface up against the axis. Okay, flat surface. So what's going to be formed are going to be these infinitely thin disks that's going to create this object that we see above. All right, so this is what I want us to do. We're going to draw the radius, and the way you draw the radius, I think this is a good habit to. Right now, it's not going to feel like a big deal, but I think later on it's going to be really helpful. Whenever you draw your radius, put your pen or pencil on the dotted line first, okay, and then from the dotted line extend to the boundary. I know right now it feels like it's like, why can't we just do it the other way from top to bottom? You can. But I think starting on the axis is always will be a good habit, especially when things get more complicated, when the shapes get more complicated, and we're going to have more than one radius to build. So if you can always start on the dotted line, then that's kind of like your anchor. You know that you're not going to be drawing it incorrectly if you always start on the dotted line and move out to the boundary. Okay, so we know that this before represented a height of a rectangle, but now that distance is going to represent the radius of these circular disks. Okay, so let's say big R of x, because we are going to have lowercase r of x, and that's going to come later, okay, for more complicated shapes. Okay, so we always do top minus bottom because we see a vertical radius in front of us. So top minus bottom, the top of the radius is hitting the root x. The bottom of the radius is hitting the y equals 0. So we say root x minus 0, which is root x. So if we're doing top minus bottom, everything that we see is going to be visually easy because everything's in terms of x. Our bounds is from where to where? 0 to 4, yep. Now, we like to put the pi out in front because it technically is a coefficient. So even though it's pi r squared, you can write it as pi r squared. I'm going to push that pi out in front. It's just a number. So definite integral from 0 to 4. We want to make sure that we square the entire radius. So square root of x quantity squared dx. Okay. Pi r squared, that's my radius, that's my area component. Dx, that's my width component. Area and width gives me that third component, that third dimension. This is going to be a 3-dimensional calculation. Everybody good so far? So I want you to just recognize that really we're taking the same information as before, we're just inserting it into a different formula, right? All right, so let's work out this problem here. What's square root of x squared going to be? Just x, right? So it's just integral of x, right? And then we go through power rule, x becomes x squared over 2. We'll evaluate from 0 to 4. And typically what I do is I ignore the pi because it's not going to impact my answer or my process. And at the very end, I just attach a pi to my answer. All right, so upper bound first. 4 squared over 2 minus 0 squared over 2. Again, just be careful with zeros. I know a lot of times 0 ends up going away, but just confirm and make sure that that you're double checking every time, right? Because it's not every case that 0 is going to end up going away for every problem. All right, 16 over 2 gives me 8. So now I say what? Units cubed. Good. 3-dimensional object. I need a 3-dimensional. Thank you. That's good. Oh, this is my second. This is my third period.
Is it? Okay, then just
Centering third, fourth. Okay, all right. So I'll keep it. Yep. Okay, so some slight adjustments, but again, we're gathering the same information like we would with area. We're just putting it into a different formula. Everybody okay so far? Okay, let's try another problem here. Back page. All right, example 2, find the volume of the solid created by 2 minus x squared, revolving around the line y equals 1. So 2 minus x squared, that's just a parabola that's going to open down with a y-intercept of 2. So sorry, I forgot to mention this. The function is 2 minus x squared, and there's another equation, and y equals, sorry, and g of x equals 1. So I have two functions here. F of x is 2 minus x squared, g of x equals 1. That's y equals 1. That's just going to be a horizontal line. So there's your shaded region. I did not get enough information in this problem. So there's a shaded region, and we're revolving it around the line y equals 1. So anytime your dotted line is flush up against a flat surface of your shaded region, you know that you're going to be doing this method, okay? Because if you can imagine, as you rotate, you're not going to see any gap or any hole. It's going to be a nice solid object. So what shape does that look like after we do rotation? Kind of like an egg-shaped object, right? Like a egg-shaped circular object. Okay, so it's a horizontal axis of revolution. From your dotted line, you're going to extend to the boundary. So this radius is a what? Vertical or horizontal? Radius is a vertical radius, right? So if it's a vertical radius, you know you can do top minus bottom, and you can keep everything the same. Okay. Below, we're going to see some problems where we're forced into a horizontal radius. If we're forced to a horizontal radius, we got to make quite a few adjustments, okay? Everything has to be in the proper form. Okay? So typically, we do a little bit more work for right minus left than we do for top minus bottom. Okay, let's go ahead and find the intersections. In this case, we really can't tell where the intersections are. We're gonna have to find them the same way that we did as we did from the previous section. We have to set the equations equal and find the intersections. So we're gonna find the bounds. So I'll set 2 minus x squared equal to 1. All right, so I'll move the x squared over to the left, subtract 1 from both sides. 2 minus 1 is 1. Next up, do what? Take the solve for x square root. So x equals what? Plus or minus 1. So we have our left and right bounds sitting here, right? -1 to 1. And we're just following this step by step. All right, let's build our radius, big R of x. Top minus bottom, we look at the top of the radius. We look at the bottom of the radius. We see what they're touching, and we just subtract them. The top of the radius is sitting on what? It's touching the 2 minus x squared. The bottom of the radius is touching the 1, so minus 1. Right now, we don't technically need parentheses, but anytime there's more than one term that comes after a minus sign, we got to protect that with a set of parentheses. All right, so my radius cleans up to be just 1 minus x squared. All right, we have everything that we need to put into our formula here. So we'll say v equals pi definite integral from -1 to 1. Big radius squared, make sure you put your entire expression. Now, if we want to solve this by hand, we have to do what? We got to do what? Not use substitution. This is a degree is small enough for us to do what? Just expand, right? So make sure right, we gotta FOIL everything out, right? FOIL everything out, and then we can do what with that afterwards? Power rule, right? FOIL everything out, do power rule, and then plug in upper lower bound. It's doable. It takes a little bit longer, but let's practice using our calculator, okay, for this. Right. So in your calculator, I like to, I mean, you can enter all this under Math 9 if you like with definite integral, but typically this is what I like to do, especially if as the problem gets more complicated. I like to insert the radius in for y1. And then I do Math 9. Again, I'm leaving the pi out of my whole calculation. I'm going to add pi manually on my own. So I'm going to go from -1 to 1. I'm going to call my radius. So if I do second trace, call y1. I'm going to take my radius. I'm going to square it. That's it, dx. Now you don't have to do it this way. You can square the radius under y1. You can put everything under here. This is just my preference. Okay. So you find the way that works for you and try this one out. If you feel like another way you want to do things, you're more than welcome to do that. Now, sometimes the calculator is able to get it to a fractional value. So we always want to test it out to see if we're able to. If we can't, then we'll just do it to 3 decimal places and add pi at the end. But here I'm going to do math fraction to see if it will change it to a fractional value for me. Sometimes it's able to. In this case, it can. any questions, any issues with the calculator? Yes, so if you get that, once you get the 1.066, go to math fraction and just test it out to see if it's able to convert it into a fraction. So math 1. Sometimes, okay, if it doesn't, then you can just do 1.07 or 1.06 pi. Right, so top minus bottom for this method is not too bad. But just understand that anytime you have a vertical axis of revolution, you got to put in some more work because the equations are most likely not going to be in the proper form. Okay, so if we want to, if we have a vertical axis of revolution, we're going to extend out and it's going to look like a horizontal radius. If we see a horizontal radius, we got to do right minus left. If we do right minus left, we have to rewrite our equations as x equals. Everything's in terms of y. Our bounds is also in terms of y. Okay. So let's look at examples 3A and B. All right, so we have the region that's formed by the function. This is y equals negative x plus 1, the x-axis and the y-axis. So go ahead and shade that region. We're going to be rotating this region here. Find the volume solid formed by revolving the region about the y-axis. Okay, so the y-axis, that's a vertical axis. Go ahead and put your dotted line up against the y-axis. So I want you to make this observation right now. Is the shaded region a flat surface up against the axis? It is, right? It's not a curved region. We don't see any gaps between the shaded region and the dotted line. So that's indication that's this method. Okay, I know we haven't learned the other washer method yet, but I just want you guys to look at that observation that it's a flat surface up against a flat line, right? Okay, so just like before, we're going to put our pen and pencil on the dotted line, and we're going to extend out to the boundary. But the only way to extend out to the boundary is horizontally, right? So if we do it horizontally, we know that, okay, I see a horizontal radius in front of me. I got to do right minus left. If I want to do right minus left, my equations have to take on a different form. So I can't use this y equals negative x plus 1. I need to rearrange it for a different variable. So if I solve for x, the equation would look like x equals what? One minus y. I move the negative x to the left side. I subtract 1 from the left to the right. You guys good? So if I add x over to the left side, I get x. Subtract y to the right side, I get 1 minus y. Okay. How about the dotted line? What's the equation of this dotted line? X equals what? All right, so we do need to find the bounds. But I think in this case, we can just look at the graph and tell, right? What's the lowest and highest? Imagine you're stacking these radius, these circular discs from down here all the way up to up here. What's the lowest and highest y value? 0 and 1. So these are your bounds. Okay, let's build our radius. Now you got to call your radius a little something different here. We're going to call it r of y because we're finding the radius in terms of y. We'll do right minus left. Okay. So right endpoint of my radius is touching which graph? 1 minus y. Minus the left endpoint is touching the 0. So 1 minus y minus 0, which can reduce to be just 1 minus y. All right, we have our radius, we have our bounds. We're ready for putting into our volume formula. Right? Make sure you put your radius in a set of brackets because you're going to have to square the whole thing. All right, and just like before, we can work this out by hand, but you get to use your calculator on the test. So we can just enter this in our calculator. So again, I like to do this. Oh, we see y's. I'm expecting y's on paper, but in the calculator, you're going to use what? X's. Okay, so go to y equals. I'm going to do 1 minus x. I'm going to square it after I get to my. Again, I'm leaving pi out of my calculator. Alpha trace will allow you to get quickly calling that radius that you have held under y1. From there, hit math fraction, math 1, see if it'll get you down to a nice fraction. It does. I think the hardest part for this entire unit is just knowing how to adjust your equation for right minus left. I think the tendency is even when students see right minus left, it's just easier to just involve how this, the same process for top minus bottom, but just anytime you see a horizontal radius, you know you have to do some additional work. Your equations are usually not going to be in the proper form. And then your bounds have to be, you have to readjust your bounds as well. We can't, I know it's also 0 to 1 in this case, but we're looking at the y values, not the x. Okay, part B. 4 minus x squared. Now this is really a parabola that extends over here. But we're only looking at this first quadrant region here. All right, we're still rotating around the y-axis. Okay, go ahead and set your pen or pencil on the axis to begin with. Also, you see, this is a flat surface up against the dotted line. So this method. Yeah. Yeah, if it's rotating around the x-axis, then it will be a top minus bottom. Yeah, but here, because it's a vertical axis, the only way that you can draw a radius is horizontally. So always start your pen and pencil on your, think of this as your anchor, and you're moving out to your region. The only way to move out to your region is horizontally. Okay, so if it's a horizontal, you know you got to make some adjustments. Your equations are not in the proper form. We got to solve for x. Okay, so again, I'm going to move things around here. X squared is equal to 4 minus y. I wouldn't do what? Take the square root. Now, these are actually two separate branches here. Which one is this referring to? So this is the positive side, right? This is the positive side, this is the negative side. So we're going to take the positive square root. Again, the y-axis takes on the equation of x equals 0. The upper bound, you can tell by looking at the graph, or you can just insert 0 into the function and solve for y. All right, find that y value there. If I plug 0 in for x, because we're talking about the y-axis here, what's that y value? 4 minus 0 squared is 4. Right, so I have everything that I need to put into my volume formula. Lowest y value is 0. Highest y value is 4. Radius, sorry, we didn't build our radius yet. R of y right minus left, the right endpoint of my radius is hitting the square root. Minus, the left endpoint is sitting on the 0. You clean that up, I can drop the 0 because it's just still going to disappear. Make our calculator do the work for us here. I can just do square root of 4 minus y. Or sorry, square root of 4 minus x. Also, the nice thing about putting everything under y1 is that you can just go up and just recall the same expression and just change a few things. Make sure you don't forget about the pi, pi's, because we're rotating. It's always going to be circle related. So we're always going to have that pi involved anytime we do rotation around an axis. Okay. Volume, so cubic units. Okay, you guys have homework from the textbook. Tomorrow, we're just going to stick with this method and just get a full day of practice moving the axis around, but just focusing on this formula. All right, let me get your phones.